record this session just because of all the uncertainty, and there may have been people who were already on their way to campus, and a lot going on this morning. So I'm going to go ahead and record this session, and then I'll provide a link to it as well. So as you can see, probably behind me, power was just restored at, I think it was 9:54 a.m. So as it turns out, we could have met here in person, but we wouldn't have known that, and it would have been 9:54 before the lights came on. So we probably made the right call in going online today. It's still disappointing. I mean, we've had one in-person session, and then we have to go online again for the second session. So it's crazy. It's a hectic schedule. I am all set up here. I'm all ready to go, even when the power is out, because for one thing, I don't know why, but the internet, the Wi-Fi worked, which is not true at my home. If the power goes out, the Wi-Fi goes out too. But it must be on the backup power supply because there is emergency lighting. So there are some lights in the hallway, and I guess Wi-Fi is a critical load, so it must be on the backup generator. So Wi-Fi was actually working. That's how I could send you the email announcements through Reginet. And then I'm kind of lucky that we've got this solar grill in the RE lab. That's why I'm here in the RE lab. We've got this solar grill, which has some giant batteries in it and an inverter in it to invert the DC electricity to AC electricity. And we got a power strip. So I've actually got everything all set up through the solar grill, and I've got everything plugged in to the solar grill. And if it can provide enough power or energy, I should say, if it can provide enough energy over about 4 hours to power the grill, then I'm confident it can power my laptop. And I had a few lamps set up also to provide some lighting. So I was like all set up and like ready to roll, even though it was dark in the building and all these lights were off. And it's also quite cold in here. I don't know how long it's been out, but it must have been out for part of the night because the heat definitely was not on. And so it's pretty cold in here. So that's another reason why it's probably good that you're all in your warm apartments anyway. But anyway, that's okay. We can roll with it. You got to roll with the punches and deal with the things that you can't control. So that's what we're going to do today. We're not going to let it hinder us too much. We had a good question. Yeah, sorry, Damien. Damien says, yeah, unless you walked all the way there and then walked all the way back. Yeah, sorry about that, Damien. I wish we could be in person. Will Tiffany, Will had a good question about the homework number 4. So I think honestly, the easiest thing to do, let's just hold on to it until Monday. I could create something in Reginet and have you submit it, but let's just hold on to it till Monday. There isn't actually a homework that is assigned today. There's not going to be a homework set on the second and third laws of thermodynamics that we talk about today. But it's still important material. It could still show up on a quiz or an exam. But since there isn't a homework assignment on it, it makes perfect sense just to hold on to problem set 4, hand that in person on Monday, and then we'll review it on Monday as well. So I will not go over problem set 4 today. Still happy to answer any questions on it, but we'll go over it in class first thing on Monday. So any questions about the schedule or about homework set number 4? All right. Okay. If not, then let's get started. If you wouldn't mind turning on your cameras, I would very much appreciate that if you can. And we're going to get started talking about the second and third laws of thermodynamics. So the second law was actually developed about the same time as the first law. You're talking like the mid 1800s by some of the same people, not all of the same people, but it was kind of a joint development between a bunch of people. Someone named Lord Kelvin was in England, and Rudolf Clausius was in Germany, and Nicolas Sadi Carnot was in France. And Carnot probably gets most of the credit, honestly. In fact, we have an equation today that we'll talk about that is actually named after him, called the Carnot efficiency. So we'll talk about that. But this was all kind of happening in like the mid 1800s around different countries in Europe. These were being developed. And then a little bit later, the first law of thermodynamics was developed around the late 1800s to early 1900s. And then the third law, which is the last one we'll talk about today, that was developed in the early 1900s. And kind of like what we talked about on Monday, we talked about the zeroth law and we spent like 2 or 3 minutes on it. And then we talked about the first law and we spent a bunch more time on it. That'll be kind of similar to what we do today, because the second law is a little bit conceptually challenging. So we're going to spend a fair amount of time discussing that and talking about the applications of that. But then the third law is super easy. I mean, we'll spend about as much time talking about the third law as we spent talking about the zeroth law on Monday. So second and third laws, that's the idea today. So like I said, the second law is a little bit challenging. I would say the second law is probably the most challenging conceptually of the 4 laws of thermodynamics. And just out of curiosity, if anybody has ever read or heard anything about the laws of thermodynamics or the second law in particular, is there a particular word, a buzzword that I know all of you have heard before that is relevant to the second law? Have you heard anything about the second law before? Starts with an E. Does that help?
I haven't learned about it before, but I just read it in the PowerPoint a bit. I read ahead and it's efficiency. Is that the word you're looking for?
It's not quite the word I'm looking for, but we are going to talk about efficiency today. So you're not wrong. I mean, we are going to talk a fair amount about efficiency today. That's true.
Gotcha.
There is one more word that also starts with an E, and it kind of sounds like what we talked about a week ago, enthalpy. We talked about enthalpy a week ago, and there's a word that sounds kind of like that is intimately tied into the second law. Anybody heard of a word that sounds kind of like enthalpy?
Entropy.
Entropy. Yeah, thank you. Well, yeah, entropy. Yeah. So we are going to talk about entropy. We'll get to that. But actually, I think one of the reasons why the second law is a little bit challenging is because there are several different ways to look at it that turn out all to be equivalent. And that's probably partly because there were a bunch of different people that were developing it at the same time in the mid 1800s, and they all came up with slightly different statements. It turns out that they are actually all equivalent, but it's not obvious that they are actually all equivalent. But we'll try to talk about them individually, these different perspectives on the second law, and then we'll try to kind of tie it all together to show that really they are all the same thing. They all just variations on the second law of thermodynamics. We'll try to show that at the very end, all right? And along the way, I'll try to show this with some analogies that make things a little bit easier to visualize. And along the way, like Duncan said, we are going to talk about efficiency because that is closely related as well. So let's go ahead and get started. I'm going to share my document camera. I got this all set up in the lab as well. I think I'm going to move it just a little bit. Okay. All right. So one of the big ideas for the second law of thermodynamics, we've talked about our basic steam cycle, right? Where we've got a boiler. We've talked about this several times now in several different classes. And then we got a steam pipe that goes over here to the turbine. And then that goes into a condenser. And then that goes into a feed pump, which pumps it back up to the boiler. All right, and we know that we have heat added in the boiler, and we're getting work out in the turbine, and we're removing heat in the condenser to condense that steam back into liquid. It's less energetic steam at this point than it is at this point, but it is still steam. And so we condense that back into water. And then we pump it in the feed pump back into the boiler, back up to a higher pressure and back into the boiler. So many people have looked at this over the past, almost 200 years. This type of thing has been around for almost 200 years. We'll talk about kind of the history of the steam cycle. I think next class. Yeah, we'll talk a little bit about that next class. But this has been around for almost 200 years. And many people have looked at that and said, this right here is a waste. This is a waste of energy. Why do I need to reject all that heat? That's energy being lost to the system. So why can't I, it's a terrible arrow, but why can't I do something instead of that? Why can't I just have a boiler and that produces steam and it goes directly into a turbine as before? And why can't I just take whatever comes out of the turbine and put that right back into the boiler? So we're actually omitting two things here, right? We're omitting the condenser, or we're thinking about, could we omit the condenser in the feed pump? It turns out that it's possible actually to omit the feed pump. That's actually not that important. There are designs actually that do away with the feed pumps. One big reason why you might want to do away with the feed pump is because it's noisy. So if you're on a nuclear powered submarine, it would be really nice if you can get away without having a feed pump. So it is possible to get away with the feed pump without using a feed pump. But the condenser, you cannot get away without using a condenser. You actually have to have a condenser. But why not? Why can't you use this system right here where you make steam by putting heat into the boiler, and then that steam goes directly into the turbine and we get work out? And then we put that, whatever comes out of the turbine, we just want to put that back into the boiler. Lots and lots of people have thought about this over many, many years, and it turns out it's not possible. You can't do this. You have to reject some energy in the form of heat in the condenser. So this does not work, but why? I mean, the question is, why not? I mean, experimentally, you can do experiments and you can show this, but it's not intuitive to understand why doesn't that work? Why can't you do that? So a couple analogies might be helpful here. And I'll show you the first analogy. This is part of the train of thought that was followed by Carnot. C-A-R-N-O-T, the French dude, French scientist who was working on this. And I mentioned this in class on Monday, but it's very helpful to recognize here that at the time in the 1800s, they didn't really know what heat was. They didn't know that heat was the vibration of atoms or molecules. They didn't know that much about atoms. They didn't know about electrons and protons and neutrons and how they bond together to form molecules. So the whole idea of thermal energy was still kind of vague to them. But one thing they did have energy conversion devices like water wheels, where like you'd have a stream that comes in and then you'd have a water wheel that is caused to rotate by the water. And then you get work out from the water wheel and you use that to grind grain or pump water, something like that, doing useful work from the flow of the stream acting on the water wheel. So that's probably actually what Carnot was thinking about as he developed his formulation of the second law of thermodynamics. Because like I said on Monday, they actually thought that heat was like a liquid called caloric that you couldn't really see and you couldn't taste it or feel it, but that they thought that's what heat was. And so Carnot envisioned something akin to like a water wheel. So think about a water wheel. This is the first analogy that I think is pretty helpful in trying to understand the second law. So here's our stream of water moving this way with some velocity. And we're going to put a water wheel in this system. So let's say we've got a water wheel, kind of like that. And then it's got these like buckets. I'm not really drawing buckets, but little spikes, and the water is going to push on these, right? It's going to push on these, and then it's going to cause this water wheel to rotate in this direction. So if I have, let's kind of connect that. So if I have a drive shaft or an axle on which that water wheel is rotating, then I can draw that out, and this is rotating with the water wheel, and that's work. That is something we can get useful work out of. I'll even kind of draw an arrow on that drive shaft to indicate that we're getting work out. We could connect that to a water pump, and we could pump water up from the ground or pump it out of a mine. That was pretty common at the time. Or grinding grain. That was also very common at the time. But after the water interacts with the water wheel, then it comes down here, right? And it's down here at the bottom of the water wheel, and we have water down here as well. So if we start to think about like an energy balance on this water wheel, we have a couple of things that we can identify. First of all, we have this moving water up here, so it certainly has kinetic energy. And we could calculate this, but we don't really need to right now. So we can just think about the fact that it has some kinetic energy. And it also has potential energy because it's some height above this reference state, if we consider this to be our reference state. So it has some kinetic energy, and it has some potential energy. That's PE, potential energy. So that's what's going into the system. And what's coming out of the system? Well, we have this work right here, but we also must have some kinetic energy remaining in the water down here, because this water, after it comes down here, it's got to get out of the way. It's got to flow and get out of the way so that the next molecule of water can come down here and replace it. So a key point to understanding this is that down here, we still have some velocity of the water. It has to, because it has to get out of the way. It has to move out of the way so that more water can replace it in this complete cycle. So you've got water coming in with potential and kinetic energy. It gives some energy in the form of work to the water wheel. It comes down here, so it's at the reference state, no potential energy, but it still has some kinetic energy. So we can do a work balance here, energy balance. We can do an energy balance And we can say that the kinetic energy plus the potential energy, and let's specify this. So let's call this kinetic energy 1 and this kinetic energy 2. That way we can be more clear about what we're talking about. So initially we have kinetic energy 1 and potential energy that's coming into our system. And that is going to equal, because energy is not created or destroyed, only converted. So that is being converted into work. And whatever's not converted into work must remain kinetic energy in the system. That's really the only options. We got work, potential energy, and kinetic energy. So if we want to solve for how much work can we get out of this system, because that's what we're after, right? We're trying to get work. We're trying to make it do something for us. So if we solve for work, I'm going to subtract kinetic energy 1 from both sides, and I'm going to subtract potential energy from both sides. So I'm going to get work equals potential energy. Oh, you know what? Sorry, I said that wrong, didn't I? So what I'm going to do is I'm going to subtract kinetic energy 2 from both sides, right? That's how I can get work all by itself on one side. Sorry, I'm just trying to solve for work and identify what the amount of work is going to be. So all I have to do is subtract kinetic energy 2 from both sides. And so I get work equals potential energy plus kinetic energy 1 minus kinetic energy 2. All right, so I just subtracted kinetic energy 2 from both sides. So I don't know what this is. I don't know what kinetic energy 2 is, but I know that it has to be greater than 0. It's not equal to 0, and it's certainly not less than 0. For our discussion right now, what Carnot's train of thought was, he knows that kinetic energy 2 has to be greater than 0. So what you could also say is that the work that you're getting out of the system must be less than potential energy plus kinetic energy 1, right? It has to be less than this because you have to subtract kinetic energy 2 from this to get work, to solve for work. So really what his line of thought was not really to solve this, but just to say, you know what, I know that I'm never going to get, I cannot possibly get as much work out as the sum of kinetic energy and potential energy into the system. All right, and that's true. That's true for a water wheel. And his kind of cleverness was in applying that to a thermal system. And it probably honestly helped that they mistakenly understood heat to be a liquid, because he really was probably visualizing heat kind of like this. And it turns out it's not, but it behaves in a kind of similar way. And you can say a similar thing about a thermal process as you can about this very mechanical process right here. That's one way of looking at it. There's another analogy that I can give you, just in case you're not real crazy about that one. Another analogy actually relates to a wind turbine. And I think all of you are at least vaguely familiar with the operation of a wind turbine. Most of you have taken Tech 160 or some equivalent to that. So we have a wind turbine, say a rotor right here. And then we have the tower right here. And let's say we have kinetic energy coming in. This is 1. Kinetic energy 1 coming in. And then this is very much like one of the problem sets that we did a few days ago. We know that that is converted into work. So it's doing work on the blades, which create a torque, which cause the whole rotor to spin, which rotates the generator, and that generator produces electrical energy. So that is work in the form of electrical energy. So we have work that is coming through the wires, actually down here. So work is coming out of the system. And at the same time, we have kinetic energy that is coming out the backside of the rotor. That's what's left over. So we can write a similar energy balance here. We can write that kinetic energy 1 equals the work plus kinetic energy 2. And if I want to solve for the work, I can subtract kinetic energy 2 from both sides. I can get work equals kinetic energy 1 minus kinetic energy 2. And I don't even have to know what any of these values are. I just have to recognize that kinetic energy 2 has to be greater than 0, because this air behind the turbine has to get out of the way. It has to move in order to make room for more air to interact with the rotor of the wind turbine. So it's sufficient here to just recognize that this term, kinetic energy 2, has to be greater than 0. And therefore, if we're subtracting a number that is greater than 0, we can say that the work must be less than kinetic energy 1. Which is to say that it's impossible to convert all of the energy input to this system into work output. It's simply not physically possible. It wasn't possible up here in the water wheel, and it's also not possible in a wind turbine. There's a certain thing that you learn about in Tech 160 that relates to the fraction of the energy input that you can extract. What was the name of that limit?
Is it Betz limit?
Exactly. Yep. Thank you, James. Yeah. The Betz limit is a theoretically derived calculation for how much can we actually get out. It turns out to be about 59%, but that's not terribly important for right now. The terribly important thing to understand right now is that it is physically impossible to get work output, to convert all of the input into a work output. So it wasn't too much of a stretch then for Carnot to envision some type of heat engine, kind of like this, but in a broader sense. It wasn't too much of a stretch for him to envision some type of a high temperature reservoir, like a tank or a body of water or any kind of liquid, anything that is at a high temperature, and we'll call that T sub H, T hot. And then we have heat coming from the high temperature reservoir into some system. And it really could be a lot of different things. It could be some type of a piston-driven steam engine, or it could be a steam turbine. It could be a lot of different things, but it's some system, and we're trying to get work out of it. So Carnot recognized that it was not possible to convert all of this energy input, we'll call that Q hot, because it's the amount of heat that is coming from the high temperature reservoir, Q hot. It's not possible to convert all that Q hot into work output, just like it was not possible to convert all this energy input into work output, or this energy input into work output. So he recognized that there has to be some left over, like the kinetic energy here, or the kinetic energy here, or in the case of a thermal system, it would be heat. And we'll call that Q cold. And that's going to a cold temperature or low. You'll see low temperature and cold temperature used interchangeably. They mean the same thing. It's just, it's colder than the high temperature reservoir was. So hot temperature and high temperature mean the same thing, and cold temperature and low temperature mean the same thing. And you'll see both. But I'm going to write cold temperature reservoir right here, T sub C, T cold. So this is some body or some tank or something that has a colder temperature than T hot. So he recognized that it's not possible. We're going to write this formally in just a second here, but he recognized that it's not possible to convert all of this thermal energy input into work output. Instead, there is going to be some left over that you cannot extract. And that is this thermal energy right here that has to be rejected, has to go to some other place, and that would be a cold temperature reservoir. All right, so we're now ready to go ahead and write the first of 3 statements of the second law. So this is the second law of thermo. And this is the version that Carnot, Nicholas Sadie Carnot came up with. And what this says is that it is impossible to make a continuously operating heat engine. It is impossible to make a continuously operating heat engine. A heat engine, what's that? Well, it's anything that's producing work as a result of heat input. All right, so it could be lots of different things, but it's some system that uses temperature. It's impossible to make a continuously operating heat engine that converts all of the heat input into work output. All right, so that is one of the 3. Actually, we'll go ahead and we'll put a circle around this like this. This is the first perspective on the second law of thermodynamics. There are 3. There are 3 ways of looking at the second law of thermodynamics, and they actually are, like I said earlier, they're actually all equivalent, even though they might not look equivalent at first. So that's one version of the second law of thermodynamics. And I gave you several examples there to kind of motivate the second law of thermodynamics from that perspective. One more thing that we can talk about and think about now as we're considering this kind of idea, this model where we've got a heat input, we've got work output, and we've got a heat output as well, is to think about efficiency again, because there are some additional things that we can say about efficiency. So first of all, we can talk about what I'm gonna call the actual operating efficiency, just to distinguish it from the other types of efficiency that we're going to talk about. So just to be very clear, this is the actual operating efficiency. So this is true of any heat engine, any thermal system that you can imagine. The actual operating efficiency is eta. Remember, we used that Greek letter to denote the efficiency of a system. And this is the same equation that we talked about last time. Nothing new here. This is the work output, that's the useful output, divided by what do you have to put in to the system? And that's the heat input. So that's Q in. All right, so this is a very useful equation. You will definitely use that. And like I said, just to emphasize this, this is the actual efficiency as the system is operating. There's nothing really theoretical about this. This is just what are you getting out that is useful divided by what you have to put into the system. So this is a general framework for defining efficiency of anything. So we can apply it to a thermal system by thinking about the work output and the heat input. If we think more specifically about a thermal system or a heat engine, then we can write an equation like this. We can say if the system operated perfectly with no friction, all right, and we're gonna make some idealizations here. This is going to be an ideal system. In an ideal world that doesn't really exist, but it's still useful and helpful for us to understand this because it's kind of an upper limit on what we can achieve. So if we say that the system operated perfectly with no friction, which of course can't exist, but we can still think about it and talk about it. No friction and no heat loss, except in the condenser where we want to have heat loss. In other words, you're going to have heat loss from all the different parts of the system. Think about a steam system, you know, like going back to the first page that we drew. If we think about this steam system, in reality, these are pipes. Those pipes are going to have heat loss. That is a loss from the system that you're never going to get back. In addition, you've got friction inside the turbine, like in the bearings of the turbine. That's friction. That's another form of energy loss. You're never going to get that back. You're also going to have heat loss from the walls of the turbine. You're never going to get that back. So these are all inefficiencies that are inescapable in the system. But we can think about a situation where we didn't have them. It makes things easier, actually. So if we had no heat loss from anywhere except in the condenser where we have to have heat loss, then we could write an equation that would actually be an energy balance. We can write an energy balance equation. And we could say that in an ideal world, in a perfect, the best we could possibly hope to achieve, the heat input that's in the boiler is going to be equal to the work output plus the heat output in the boiler. And you might be saying, oh, what about the feed pump? So a couple things. So like I said earlier, you can actually get away without having a feed pump. It's not common. And it usually makes the system work better if you have a feed pump. But you could actually design a system where you have a gravity feed from the condenser into the boiler. It's not common, and you have to design the system differently because your pressures would be different. But you don't actually have to have a feed pump. You just, in practice, almost always do. So you can think about that. Or if you prefer, you could actually think about this work as the net work, not the network, but the net work. You see what I'm saying? You can think about that as the network, that is the work output from the turbine, and subtract the work input in the feed pump, if you want to think about it that way. But it's fine either way. But our major energy inputs and outputs are the heat input in the boiler and the energy out as work from the turbine or the piston and cylinder arrangement, whatever arrangement you've got, and the heat output in the boiler. So again, we're interested in this, the work output. So we want to rearrange and solve for the work output. So we can say the work output equals the heat input minus the heat output. Again, this is an ideal world, perfectly, ideally operating system. And we can do a little bit more of manipulation, and we can convert that into an efficiency by dividing both sides. I'll write right here what we're going to do. We're going to divide both sides by Q in. And if we do that, you can see that when I divide this side by Q in, it looks like efficiency, right? It is efficiency. So I'm going to go ahead and do that. We're going to divide this side by Q in, and we're going to divide this side by Q in. What you do to one side, you have to do the other side. So what I've got over here on the left side is actually efficiency. It's not the efficiency of an actual operating system, you know, because these are based on like measurements from an operating system. This would be the efficiency in an ideal world for a perfect system that has no heat losses or friction, except for the heat loss in the condenser, which is Q out. All right, so I can replace this with my variable for efficiency. Just remember that efficiency is not the exact same thing as the actual operating efficiency. So if you're trying to measure the actual operating efficiency of a system, that looks like this. You measure the work output, you measure the heat input, and that's what the actual efficiency of the system is. We've got a question. Is there a question?
Yeah, is theta supposed to be efficiency? Is that like universal for this class?
Yeah, it pretty much is. This is eta. It's not theta.
Okay.
Theta, I'll draw up here. Theta looks like this.
Oh, yeah, right.
Whereas eta, ETA is how you spell eta. Eta looks like this. And that is, yeah, pretty much always in this class and universally in the fields of thermodynamics and heat transfer, thermal sciences, you're going to see eta universally as efficiency. Yeah, good question.
Awesome. Thank you.
Sure. All right, so eta is our ideal efficiency. We'll have a better name for it in a little bit, but our efficiency equals Q in minus Q out divided by Q in. And we can do a little bit more algebra on this. When you have something subtracted in the numerator like this, and they're both they're divided by this value in the denominator, we can separate these. That is legal in the laws of algebra. And so we can write this is equal to Q in divided by Q in minus Q out divided by Q in. All right. So you can probably see here, this term right here, Q in divided by Q in, it doesn't matter what Q in is. If we're dividing a number by itself, it's equal to 1. So we can rewrite this a little bit more cleanly, and we can say that the idealized, or we're going to actually call it the Carnot efficiency, is equal to 1 minus Q out divided by Q in. So this is a good equation to know. This is called the Carnot efficiency. And it's kind of like an upper limit. In the same way that the Betz limit is an upper limit on the efficiency of a wind turbine, the Carnot efficiency is the upper limit on the efficiency of any kind of thermal engine, any kind of heat engine, any kind of engine that uses heat to do work, which would include all kinds of internal combustion engines and steam cycles and all the power plants that we talked about initially that we said this could apply to, biomass plants and solar thermal plants and nuclear and coal and natural gas and lots of other stuff too. Anytime that you're using heat to do work, this is the efficiency that applies. But there's one more thing that I'm going to do to it to make this more useful. It's often pretty difficult to measure Q out and Q in. It's difficult to have a meter that measures Q out or Q in. That's difficult, not impossible, but that's difficult to measure. So as it turns out, and this actually is related to heat transfer that we'll talk about in a couple of weeks, but as it turns out, the heat that is transferred, that's Q. So Q out and Q in, all the heat transfers are proportional to, that's a Greek letter alpha, it means proportional to in all different areas of science. Alpha means proportional to. The amount of heat that is actually transferred is proportional to the temperature difference. So by knowing something about the temperatures, say of the high temperature reservoir and the low temperature reservoir, we can actually use that as a proxy for the heat output and the heat input. That might not be obvious right now, but think about this. I used the example of like my hand and I put it on the desk on Monday, right? So if the temperature difference between my hand and the table is 0, if my hand temperature is at the temperature of the table, which feels like it's pretty close right now because it's freezing in here, there's no heat transfer. There's no heat transferred if there's no temperature difference. If there's a very low temperature difference between my hand and the table, then when I put my hand on the table, there's a little bit of heat transferred. If my hand was really hot and I put my hand on the table, then there's a large temperature difference between my hand and the table, and therefore there would be a large amount of heat transfer between my hand and the table. So basically what I'm saying is the amount of heat that is transferred is always proportional to the difference in temperature between the things that we're talking about, that we're transferring heat from one place to another. So what we can do, and this might not seem obvious right now, but because this is proportional, it's linearly proportional, what we can do is we can replace Q out by the low temperature, and we can replace Q in by the high temperature of the reservoirs. So this equation, it turns out, is actually a lot more useful. It's easier to use. The Carnot efficiency, it's still called the Carnot efficiency. It's equal to 1 minus T sub L, which could also be written T sub cold. Like I said, T sub L is the same thing as T sub C. It refers to the lower or colder temperature reservoir, divided by T sub H. That is the temperature of the high temperature reservoir, or hot. It's actually kind of convenient that high and hot both start with H. So you'll see T sub H for the high temperature, and you'll see either T sub L or T sub C, depending on context, and different textbooks write it different ways. But that is the temperature of the low temperature reservoir. So this is another very useful equation. And this is also called the Carnot efficiency. It's the same thing. So these are two different expressions for the same thing. It's the Carnot efficiency, which is the upper limit of the efficiency of a thermal engine. Anything that is producing work using heat. This is the maximum efficiency that you can ever achieve. All right. Oh, one more very important thing about this. I'm glad I just remembered to say this. So when you're measuring temperature in these, you have to remember to use absolute temperatures. Use absolute temperatures, which means that we use the Kelvin temperature scale. So if you don't remember, to get a temperature in Kelvin, you take, here, I'll write this down. So if you want to find the temperature in Kelvin, and we don't really talk about degrees, that's just not the, that's not the nomenclature that's used for Kelvin, but the temperature in Kelvin equals the degrees Celsius plus 273. Actually, to be really, really precise, I think it's 273.15, I think, if I'm remembering right, but that's close enough. Temperature in Celsius, degrees Celsius plus 273, that gets you the temperature in Kelvin. So freezing temperature of water at atmospheric pressure, 0 degrees Celsius, add 273. So the freezing temperature of water is 273 Kelvin. All right. That's really important when you plug those in. If you plug in these temperatures in Celsius or Fahrenheit or any other temperature scale that's not an absolute temperature scale, they're going to be way off. It's going to be very inaccurate. All right. Any questions so far? All right, so that's one way of looking at the second law of thermodynamics. That is the first statement of the second law of thermodynamics, and these are some implications of it, including the Carnot efficiency. The second and third ways probably won't take quite as long to discuss. Let's go ahead and start in on the second perspective or second way of looking at the second law of thermodynamics. In the first way, I gave you some examples and then we summarized it. We wrote the first way of looking at the second law. I think this time I'm going to go ahead and write it. I'm going to go ahead and write the second way of describing the second law of thermodynamics. And this way was popularized or discovered by Clausius, Rudolf Clausius, the German. So the way that he described this is to say that it is impossible to make a continuously operating device, to make a continuously operating device whose only effect, so that means the only thing it's doing, whose only effect, it is impossible to make a continuously operating device whose only effect is to transfer heat from a lower temperature reservoir to a higher temperature reservoir. From a lower temperature reservoir. When I say reservoir, you can think of a body, you know, like something that is colder. That's what I mean by a lower temperature reservoir. From a lower temperature reservoir to a higher temperature reservoir. All right. Whose only effect, all right? So it is impossible to make a continuously operating device whose only effect is to transfer heat from a lower temperature reservoir to a higher temperature reservoir. What does that kind of mean? Well, it means that heat will never spontaneously flow from something that is cold to something that is hot. That's what that means. You can make heat transfer from something that is cold to something that is hot, But if you want to do that, then you have to provide work input. You have to create this system that will pump the heat from the cold temperature reservoir to the high temperature reservoir. And that is not a system whose only effect is to transfer heat from a low temperature to a high temperature reservoir. So we kind of talked about this a little bit last time. We talked about a thermodynamic systems where, let's say, we have a high temperature, and then that high temperature goes into some thermodynamic system, and then we have work output, and then we also have heat rejected to something that is colder in temperature. That's our standard steam cycle that is mainly the subject of this class. But what this is saying is that you're never ever going to, if you disregard this work, you're never going to get a system that, I'll go ahead and draw it. You're never going to be able to have a system that looks like this. This cannot happen. That's what this is saying right here. It's impossible to make a continuous operating device whose only effect is to transfer heat from a lower temperature reservoir to a higher temperature reservoir. The only way you can do that is by adding work into the system. So if you're adding work into the system, this becomes a heat pump, like an air source heat pump or a refrigerator or an air conditioner, something like that. You can do work on the system, and through work on the system, you can transfer heat from a lower temperature to a higher temperature reservoir, but it's not going to happen spontaneously. And there is another effect, and that is adding the work here. So this does not violate this statement up here. All right. There's another concept that we need to introduce now that's relevant to this idea, and it ties directly into the third way of looking at the second law of thermodynamics, and that is the idea of reversibility. Reversibility. It's not a word that I use every day. Or you can also think about it as irreversibility. Irreversibility. That's probably the longest word I'm going to spell today, probably. So the reversibility or the irreversibility of a system. If you think about these two systems, look at this. They are doing the exact opposite. All the arrows are going the exact opposite direction. So what if I could design a system that works like this for a while, like an hour or whatever, and I am transferring heat from some, maybe like a tank of hot water over here to a tank of cold water over there, and I'm getting work out of it in the process. And then after a certain period of time, then I want to reverse the system and operate it like this. So yeah, I have to provide work input to the system, and I want to transfer the heat from the cold temperature reservoir back to the high temperature reservoir. So the idea could be, if you're thinking about this, maybe I could use all the work output from this system when it's operating like this. I could use this work output, and then at the end of whatever time period, maybe I can reverse it by taking that work output and using that as work input right here, and reverse everything and end up exactly where I started. Because maybe, hypothetically, maybe I could take all this work output and take that exact amount of work that I got out and turn around and put that in as work into the system and completely reverse this system and bring it back to its original state without any loss of energy whatsoever. So if you can probably guess that that's not possible. It's not possible to completely reverse the process without any energy loss whatsoever. You can't run this system for an hour and then reverse it and then end up exactly in the same state without any energy loss. That's how it works out. You actually cannot do that. But that has to do with the idea of reversibility or irreversibility, which is relevant to this statement. And it's also relevant to the third way that we're going to talk about, the second law of thermodynamics. So what can we say about reversibility? We can say that if a process, and again, by process, we're talking about whatever's in here. It's probably some contraption consisting of pistons and cylinders, or turbines and condensers and pumps and boilers, whatever, lots of stuff. Whatever thermal system is contained in this circle right here. So if a process operates perfectly with no friction or external heat loss, if a process operates perfectly with no friction or external heat loss, that is, we don't have heat lost through the pipes or through the walls of the cylinder or the walls of the turbine. We only have heat going from here to here and here to here. So if a process operates perfectly with no friction or external heat loss, then the process is reversible. Then the process is reversible. And that means the direction of the heat and work flows can be reversed. The direction of the heat and work flows can be reversed and all energy recovered. And all energy recovered. But let's make this just a little bit longer to make it more realistic. But if there is friction or heat loss, which there always will be in real systems, if there is friction or external heat loss, so if this high temperature reservoir is actually experiencing heat loss to the ambient environment, which it is, and if this piping is experiencing heat loss to the environment, which it is, and if there's friction in any of the mechanical components in there, which there is, then the process is irreversible. So, but if there is friction or external heat loss, then the process is irreversible. All right, so what do we mean by irreversible? It's not that you can't do it. I mean, I actually briefly discussed on Monday the idea of an air source heat pump for a home. You can actually have a system where you run it as an air conditioner during the summertime, and then you literally reverse the flow of everything and you turn it into a heat pump in the wintertime. So you're actually pumping the heat from the outside to the inside of your home in the wintertime, whereas it's just an air conditioner. An air conditioner pumps heat from inside your home to outside your home in the summertime. So you can do that. I mean, you can have a system that is reversible like this, but when we talk about reversible in a thermodynamic sense, we mean there's no energy loss. All right, so you could do this for a while and then switch it and do this, but the work that you have to provide here as input will always be greater than the amount of work that you got out of the system. So this is in the real world, if this is a real world system, it's actually irreversible. It's an irreversible system because you're not going to recover all of the energy that you got out. You're not going to be able to restore it to its original state without any energy loss. All right, does that make sense? All right, it's 11:06 right now. That's kind of a good place to take a pause. And we'll come back in 5 minutes and we'll finish this idea, which is almost finished. And then we'll move on to the last way of looking at the second law. And then very briefly, we'll talk about the third law of thermodynamics. So it's 11:06 right now. Let's come back at 11:11 and finish things up. All right, I'll see you then. All right, I'm back. I'm still running off of the electricity from the solar grill. I just checked the voltage. It is going strong. It's a 48 volt nominal system. It's four 12-volt batteries wired in series. And the current voltage of the system is actually 49.6 volts. So it's still good. It's still maybe not fully charged, but it's mostly charged still. So that's good. And that makes sense since it's designed to power that grill for a long time. It's not surprising that it has no trouble powering my laptop and some lights. I considered having that power the projector for class, but I don't know. I don't know if that would work well or not. And I don't know if I'd also have to power that rolling AV cart also, probably. I don't know how it all ties together. So it's probably better that we just did it this way. So we're going to continue our discussion of the second law. And I've got a couple of slides after we're done, kind of like we did last time, where just a quick review, and then I've got some perpetual motion machines of the second and third kinds that we'll talk about today. So let's go back to the document camera. All right, so we were talking about this idea of reversibility and irreversibility. And as it turns out, in nature, mix things up. I'm using green now. In nature, perfectly reversible systems don't exist. There's no such thing in the real world as a completely reversible systems. In nature, perfectly reversible systems don't exist. There's always losses. Most notably friction and heat loss to the environment. Friction and heat loss to the environment. That is, heat losses to external to the system. Heat losses to something outside of the system, like the ambient air through the piping or something like that. There are always losses, which means that there's no such thing as a truly reversible system. If you want to make a system work as reversibly as possible, then what you would do is make it work as slowly as possible. So like your piston inside of a cylinder, if you move the piston as slowly as possible inside the cylinder, then you'll get it close to being reversible. To truly make it reversible, it would have to move infinitely slowly, which basically means not move at all. And if it's not moving at all, then there's no work output. So that's not useful, right? So to make a useful system, you have to make things move at a reasonable speed. And if they're moving at a reasonable speed, there's going to be friction and there's going to be heat losses. So that's why in the real world, everything is irreversible. There is no such thing as a reversible system in the real world. But we do have a measurement of how irreversible it is. To measure the irreversibility, with a particular unit that we call entropy. Entropy is the measurement of how irreversible a process is. So entropy, it is a pretty quick and easy definition, even though it's a pretty vague and nebulous concept, but the definition is pretty easy. The entropy is a measurement of the disorder of a system. Measurement of the disorder of a system. So the example that's often used is like your bedroom when it's dirty it has more entropy than when it's clean. When it's all organized, it has low entropy. When it's messy and stuff is scattered all about, it has a high entropy. And the world gradually is evolving toward a system with more and more and more and more entropy. In fact, the entire universe is evolving toward a system that gradually has more and more and more entropy, because in nature, there are no reversible systems. Everything is irreversible. And as we make those irreversible systems, it's not just us, I mean, it's the entire universe. As heat is being transferred around the universe, those are irreversible processes, and entropy is created through those irreversible processes. So in a sense, as the entropy is increasing, the whole universe is gradually kind of exploding. It's exploding, it's becoming more and more disordered. I distinctly remember learning about this when I was an undergrad in college, and talking to my professor about this, and trying to come to grips with this term, and asking him, so the entire world is exploding? I mean, is that what you're saying? And he said, yes, the whole world is exploding. He was like a German guy, and he talked with an accent kind of like that, and that just always stuck with me, because I didn't think that was like made sense, like the world is exploding, but it is actually. That is the correct interpretation of this. All processes in nature are irreversible, and irreversible processes cause entropy to increase, which means more disorder. It's more chaotic. It's like an explosion. It's like the world is gradually exploding. So that's kind of how this actually does work. There is an equation for entropy that I want you to know, although we're not going to use it very much. The entropy is the variable S. That's the standard variable for entropy. The change in entropy of a system is equal to the heat that is transferred divided by the temperature at which it is transferred. So you think about the temperature of the heat that is being transferred, that would be T, and the amount of heat in kilojoules or whatever, that would be Q. So this is the equation for entropy, but we're not really going to use it a whole lot in this class. I just want you to know it. It could be useful for you to know. So now we can go ahead and we can write the third and final statement of the second law of thermodynamics. So this is the third perspective of the second law of thermodynamics, and that is the total entropy of an isolated system always increases over time. Always increases over time, or remain constant for, or remains constant for an ideal or reversible system. For an ideal, I'll put in parentheses, reversible system, which we know don't exist in the real world. So the total entropy of an isolated system, so take any system, draw a boundary around it, that's an isolated system. The total entropy in an isolated system always increases over time, or it remains constant if you have an ideal or reversible system. So this is only a hypothetical construct. It's only helpful to think about this like best case scenario. So best case scenario, you have the Carnot efficiency. Best case scenario, your change in entropy is 0. but you will never, ever, ever have a decrease in entropy. You'll never, ever, ever have a decrease in entropy. All right, so that's the third way of looking at the second law of thermodynamics, because yeah, so if it's a system that exists in nature, it is irreversible, and therefore the entropy is increasing. So let's take a look at a little example here. And I want to try to show you that these all do tie together. These three different ways of looking at the second law. They seem very different, I know, but they actually all get at the same thing. So let's take a hypothetical example where we have a high temperature body, and let's say we're going to try to put that into a system, let's say a turbine. So I've got a turbine right here, and I'm going to have work output. And let's say I want that to be it. So we know that this is going to violate the first way of looking at the second law. So this violates the first way. Let's see if it also violates the third way of looking at it with regard to entropy. So here's our isolated system. So if they are consistent, if the ways of looking at the second law are consistent, then if it violates one way of looking at the second law, it should also violate another way, the other ways of looking at the second law of thermodynamics also, right? So we have all of our heat that's being transferred from T hot to the turbine. All that heat is being converted to work output. So we're not having any other losses. We're not losing any heat. We're not even absorbing heat by the turbine. All of this heat is going directly to work output. So we have the change in entropy of an isolated system is equal to the heat transferred divided by the temperature that it's transferred at. And in this case, we've got three different processes, actually, three different things to consider. So we have the change in entropy for the total system is equal to the change in entropy for this reservoir, that high temperature body. The change in entropy of the reservoir plus the change in entropy of this device. It's a turbine. I've drawn it as a turbine, but whatever it is, change in entropy of the device plus the change in entropy of the environment, like this area out here, what's around it. I'll put E and V for environment around this system. So we can actually fill this in. So delta S equals the change in entropy of the reservoir. So we are having heat leave this reservoir. So we have a negative Q. Doesn't really matter what that is. I'm not going to use numbers because it doesn't really matter. We can prove the point without even using numbers. So we have Q, whatever that is. We have Q leaving T hot, and it's at T hot. So that is the change in entropy of the reservoir. Then we think about the change in entropy of the device. The thing is, there's not being heat transferred to the device itself. It's not warming up. The device itself is not having heat transferred to it. The heat that is right here is being converted directly into work without the device itself actually absorbing any energy. So this heat is actually going directly into work. It's not going to the turbine, it's going directly into work. So this is the turbine or the device itself. And we're not actually transferring heat energy to the device, we're transferring it directly into work. So the change in entropy of the device is actually 0 because there's no heat going to the device itself. The heat is all going to work. So the change in entropy actually is 0 for the device. And if we think about the change in entropy of the environment, well, the only thing going to the environment is work, not heat. there is no Q going to the environment. So if Q is 0, then the change in entropy is also 0. So the total change in entropy of this system, this hypothetical system, is negative Q divided by T hot. Q is not going to be a negative number. T hot's not going to be a negative number because it's an absolute temperature value. So this is going to be a negative number. So this cannot happen. This violates the second law. And it violates the second law because of several different ways of looking at the second law. So if it violates several different ways of looking at it, they're consistent, right? So that'd be a good thing, right? So it violates the third way of looking at it because it said the total entropy of an isolated system always increases over time or remains constant for an ideal system. We said that if this could happen, then what that would give you is a negative change in entropy, and that cannot happen. So this violates this statement of the second law of thermodynamics, and it also violates the first way that we talked about, which is to say it's impossible to make a continuously operating heat engine that converts all of the heat input into work output, which is what we were trying to do here. So it's not a surprise that it violates the second law, both of these statements of the second law. In fact, it's kind of reassuring that if it violates this statement of the second law, that it also violates the first statement of the second law, because that means they're consistent. And so that's kind of reassuring to know that they are consistent. So we can kind of say that they agree. The different statements of the second law, they do agree. All right. Any questions about the second law? That's actually it for the second law of thermodynamics. The third law of thermodynamics. Let me get a new piece of paper. It's pretty straightforward though. It's pretty simple. There's not a whole lot of discussion here. Third law of thermodynamics has to do with entropy, which is why it's the last one, because it builds on the second law of thermodynamics. It says that the entropy of a perfect crystal What is a perfect crystal? Well, if you take Tech 293, which most of you probably won't, but I teach that class as well. A crystal is a perfectly ordered lattice structure. It's a structure in which you have a perfectly ordered and repeated sequence of atoms or molecules. So think about like a three-dimensional structure where you have these rows and columns in 3 dimensions of atoms or molecules, and it's perfectly ordered and perfectly repeated throughout the entire structure. That's sometimes called a crystalline lattice structure. So if it's a perfect crystalline structure, which usually it's not, because usually there's defects and there's imperfections in the crystalline structure. But if it was, if you did have this perfect crystal structure, then the entropy, that is the disorder, in a perfect crystal at absolute 0 temperature is exactly equal to 0. Right? The entropy of a perfect crystal at absolute 0 temperature is exactly equal to 0. So what does this do for us? You know, there's not really an equation we can pull out of this. It's really just like a ground state, a ground or a reference. It's like a ground state for entropy. Just kind of like absolute 0 provides a ground state for temperature, right? So we got a ground or an absolute reference value for temperature, and this gives us an absolute reference for entropy. If you got something, an object of some sort, and it's not a perfect, if it's not a perfect crystalline structure, it can never have zero entropy. And if it's not at absolute zero temperature, it can never have zero entropy. So in the real world, nothing in the real world is ever a perfect crystalline structure, and nothing in the real world is ever actually at absolute zero temperature. So in the practical sense, it's more of a construct that just gives us this reference state, this ground state for entropy. That's what zero entropy means. That's it. That's all the third law is. Like I said, that one's really quick and easy, especially compared to the second law. So are there any questions about the second or third laws? Like I said, I do have a few slides that I want to show you. They're kind of like the slides that I showed on Monday. It's just a little bit of quick review and then some perpetual motion machines. All right, if not, then I'm gonna go ahead into my slides. All right, and I'm gonna go through the first of the slides pretty quickly because it's just review, what we just talked about. So these are all the statements of the second law that we just talked about in some level of detail. You can't make a continuously operating heat engine that converts all the heat input into work output. You have to reject some heat. That's why you have to have a condenser. It's also impossible to make a continuously operating device whose only result is to transfer heat from a lower temperature body to a higher temperature body. You can do that, but you have to have work input. It's not going to spontaneously happen. And lastly, the total entropy of an isolated system always increases over time or remains constant for an ideal or reversible system. So here are some equations that we talked about. Nothing new here. We went through all of these. We said that the work output is always going to be less for the heat input. And that's true even for reversible processes. If you have an ideal or reversible process, then your change in entropy is zero. For a real irreversible process, your change in entropy will always be greater than zero. We call this our actual operating efficiency. If you can measure that and you can measure that for a real system, you can get the real operating efficiency. So that is a general term for efficiency. And you can talk about the Carnot efficiency. That's for an ideal system. It's perfect, no friction, no heat losses, it's reversible. You can say that it's equal to 1 minus Q out divided by Q in. You can replace Q out with the low temperature reservoir, and you can replace Q in with the high temperature reservoir, because in heat transfer, and we'll see this later on, in heat transfer, the amount of heat transferred is always proportional to the difference in temperature. So we can just make that one-for-one substitution, which makes it a lot easier because we can measure that and that really easily, a thermometer, whereas it's much harder to measure that and that. All right, perpetual motion machines. So like the first kind of perpetual motion machines, the patent office is supposed to prevent any of these perpetual motion machines from being patented. They reject them. And so if it violates the second law of thermodynamics, then it's called a perpetual motion machine of the second kind. So I have a few examples here. The first one is obvious. We drew this a couple of different times. So if it converts all the heat energy input into work output, it's a perpetual motion machine of the second kind. Even if you add a pump in there, it doesn't really change anything. The net work output, so you can take the turbine work out minus the work into the pump, the net work output always has to be less than the heat input, which is this. This is kind of a long statement, but it is kind of a famous thought experiment. So I'll give you a minute here to read this. It's called Maxwell's Demon, named after James Clerk Maxwell, the scientist. All right, so it's this hypothetical atomic scale thing that can somehow exclude all of the high temperature molecules from entering a room, whereas allowing high temperature molecules that are in the room to pass out of the room. And so thereby it actually acts as an air conditioner that doesn't need any power supply. So this would violate the second law of thermodynamics. And it would violate it because it doesn't use any energy. It's not using any energy. It violates the second way that we looked at the second law of thermodynamics. It requires a work input. It requires a work input to pump heat from a lower temperature reservoir to a higher temperature reservoir. So if this is lowering the temperature in one room by raising the temperature in another room, then it is violating the second law of thermodynamics. And this example violates it because it's not requiring any work input. So an air conditioner does not violate the second law because you're providing work input to pump heat from a cold temperature reservoir like a refrigerator to a high temperature reservoir like your kitchen. Here's another one. This is pretty interesting and pretty cool. It was popularized by a guy named Richard Feynman, who's dead now, but he was a professor at Caltech for a lot of years in the latter half of the 1900s. And this is something that he talked about sometimes. The idea is that you've got these sealed or isolated cubes. And in this one, you've got a paddle wheel. And inside here, you've got air. And air has random motion all over, right? We've got these air molecules and they have random, it's called Brownian motion. Brownian motion is the random motion of the molecules, especially inside of a gas. And so those random molecule motions will act on this paddle wheel in both directions. They'll try to turn it clockwise, and they'll also be impacting it from the other side to try to turn it counterclockwise. Over in here, in a separate cube, you've got a ratcheting mechanism, kind of like a ratchet like on a wrench, where you can turn it in one direction, but not the other direction. And so what this would purport to do would be to allow rotation of this whole apparatus in what looks like the clockwise direction, but prevent it from rotating in the counterclockwise direction. And so once again, this is a violation of the second law of thermodynamics. And the reason is because there's not necessarily a delta T in between here, a temperature difference. If there was a temperature difference between here, then that would be the driver of the work that's being done. But if there's no temperature difference between here, then this cannot work. And it's a violation of the second law. What you actually get is you'd get Brownian motion, not only of the paddle wheel, but you'd also get Brownian motion of the ratcheting mechanism as well. So this could not work on an atomic level. You cannot make a ratchet that works at the atomic level because there's random Brownian motion that acts at the atomic level and would cause that to not prevent motion in the other direction. So it would work in both directions, thus invalidating the whole thing. Here's another one. It's the same thing. It's a Brownian motor working on Brownian motion, the same idea with a ratcheting effect over here. But once again, a ratcheting effect cannot work at the atomic level because there's Brownian motion acting on both directions, acting on both directions of this ratchet mechanism. So it would not prevent rotation in either direction. So once again, this can't work. There is a third kind of perpetual motion machine that I want you to know about. The third kind's a little bit different than the first and second kinds. The third type of perpetual motion machine does not mean that it violates the third law of thermodynamics. Whereas the first kind of perpetual motion machine violates the first law, the second kind of perpetual motion machine violates the second law of thermodynamics. The third kind of perpetual motion machine just ignores friction or anything else that is dissipative. So we know that over time, energy will dissipate to the environment, to other objects that are nearby, and you're not going to avoid that. You can never avoid that. So if something runs forever simply because there's no friction, that would be a perpetual motion machine of the third kind. So here are some examples. You got a flywheel that just keeps on spinning at the same speed without any energy input. That would be a perpetual motion machine of the third kind, because there will always be some friction or drag. Or if you've got like a U-shaped track and you drop a marble on one side of the track, if the marble rolls back and forth and it always returns to its original height, that means it never lost energy in the form of friction. So it's just converting from potential to kinetic to potential to kinetic to potential to kinetic to potential. If it always comes back to the same height as it started, then it doesn't have any friction. And that would be a perpetual motion machine of the third kind. Or if you have a bouncing ball, like a bouncy ball, and I drop it and it bounces off the floor and it comes back to the exact same height, then that too would be a perpetual motion machine of the third kind, because in reality, there's some friction. The friction in this one actually comes from the compression of the rubber ball. And there's friction internal to the ball. When it hits the floor, it will compress that ball a little bit. And then it will spring back, and that's what causes it to recoil back up. But when it does that, there will be internal friction inside that rubber ball. So it'll never come back to the same height. If it does, then it's a perpetual motion machine of the third kind. So here's a summary of perpetual motion machines. This is the last slide for today. If it gets something from nothing, or you have this unlimited free energy, then usually that's an indication that it's a perpetual motion machine of the first kind. It violates the first law. If it's converting heat into work without rejecting any heat to a colder temperature, then that is a perpetual motion machine of the second kind. It violates the second law. And if it eliminates any friction or dissipative losses, so it can operate forever, then that would be a perpetual motion machine of the third kind. So just remember that perpetual motion machines of the third kind don't necessarily violate the third law of thermodynamics. So they're a little bit different. It's kind of fun to think about, though. I think it's kind of fun to think about perpetual motion machines and ideas for free energy. Unfortunately, it's never been found. There's never been a source of free energy that's been found. So that's it for today. We've covered the second law in some level of detail and the third law in just enough detail. And there really is no homework set. There's no problem set about the second and third laws. So that's nice, right? So if you've already done problem set number 4, then there's no homework for Monday. Like I said, we will review problem set number 4 on Monday in class, and we'll just hand in problem set number 4 at the beginning of class on Monday. All right, so that's all I've got for today. Any questions for the class as a group? All right, if not, I'll stick around on Zoom for a few minutes in case there are any individual questions, or if not, then have a good weekend and I'll see you on Monday.
So I have a question regarding my homework.
Yeah, I'm sorry for the miscommunication, Melker. That was
Uh,
sorry about that. It's hard for me to, especially at the beginning of the semester, it's hard for me to keep straight who's in what class. So
yeah,
sorry for
no
the-
worries, no worries. I was just wondering if I'm gonna turn in both chapter 3 and 4 on that Monday, or do you want me to send you chapter 3 now?
Either way, whatever is most convenient for you. If you want to turn it in on Monday, that's fine.
Okay, yeah. Yeah, I'll just do it on Monday.
Okay, all right, sounds
Thank you.
good.
Have a good one.
You too.